Look up at the night sky. What do you see? A scattering of stars, perhaps the glow of a distant planet, or the silent dance of the Milky Way. But behind that familiar curtain of darkness lies a universe teeming with secrets so profound, they could rewrite everything we think we know about reality itself. Scientists are uncovering discoveries at a pace that defies imagination, each one peeling back another layer of the cosmos, revealing truths more astonishing than fiction. From rogue planets drifting between galaxies to black holes that shouldn't exist, the universe is shouting its mysteries louder than ever, and we're finally starting to listen. This isn't just about distant specks of light or abstract equations scribbled on a chalkboard. These breakthroughs strike at the heart of what it means to be human in a vast, evolving cosmos. Imagine standing at the edge of a cosmic revelation, one that could redefine life, time, even the very fabric of space. What if we're on the verge of finding answers to questions we've barely dared to ask? That's the thrill of this moment. Every telescope, every probe, every flicker of data brings us closer to truths that might shatter our oldest assumptions or confirm our wildest hopes. And that's exactly what we're diving into today. 30 jaw-dropping discoveries that could change everything. Some will make you question reality, others might ignite a spark of wonder you haven't felt since childhood. We're talking about celestial anomalies that defy physics, hidden forces bending the universe in ways we can't yet explain, and clues that hint at realities beyond our own. This isn't just a list, it's a journey to the edges of knowledge, where the known universe meets the unimaginable. So buckle up. By the time we're done, you'll never look at the night sky the same way again. The first mystery on our list isn't just strange, it's downright otherworldly. In 2017, astronomers spotted something streaking through our solar system that defied all expectations. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar, and from the moment it appeared, this interstellar visitor shattered every assumption we had about cosmic debris. Unlike any asteroid or comet we'd ever seen, Oumuamua was shaped like a flattened cigar, tumbling end over end as it raced past the sun at nearly 200,000 miles per hour. But the real shock came when it did something impossible. It accelerated. Comets speed up when their icy surfaces vaporize in sunlight, creating a visible tail. Oumuamua had no tail, no dust, no gas, nothing to explain its sudden burst of speed. Scientists scrambled for answers. Maybe it was made of exotic hydrogen ice that left no trace. Or perhaps solar radiation pressure alone pushed it forward, a theory so unlikely it raised more questions than answers. Then came the bombshell suggestion from Harvard astronomer Avi Loeb. What if Oumuamua wasn't a natural object at all? Could its acceleration be the result of a thin, light-powered sail, the kind we've theorized for our own interstellar probes? The debate still rages. Mainstream science leans toward rare natural explanations, but the truth is, we may never know for sure. By the time we noticed Oumuamua, it was already leaving our solar system, taking its secrets with it. What's undeniable is this: it came from another star, carrying properties unlike anything born in our cosmic neighborhood. Was it a bizarrely shaped space rock, a fragment of a shattered alien world, or something even more extraordinary? One thing's certain: Oumuamua forced us to confront a humbling reality. The universe is far stranger than we ever imagined, and it's sending us hints we're only beginning to decipher. Venus has always been the hellish sibling of Earth, a world where surface temperatures soar past 800 degrees Fahrenheit and crushing atmospheric pressures rival the depths of our oceans. Its clouds, not much better, a toxic brew of sulfuric acid swirling in winds that could shred a skyscraper. But in 2020, astronomers dropped a bombshell that made everyone rethink this planetary inferno. They found phosphine, a gas that on Earth is only produced by microbes thriving in oxygen-free environments like swamps or industrial labs. The discovery sent shockwaves through the scientific community because, in theory, phosphine shouldn't exist in Venus's atmosphere at all. There's no known geological or chemical process on Venus that could create it in the quantities detected, at least, none we've discovered yet, so how did it get there? One tantalizing possibility: life, hardy, airborne microbes floating 50 kilometers above the surface, surviving in the planet's relatively temperate cloud layers, where pressures and temperatures are almost Earth-like. It's a wild idea, but not impossible. On Earth, extremophiles thrive in volcanic vents, radioactive waste, even the vacuum of space. Could Venus's clouds harbor similar survivors? The debate exploded. Critics argued the phosphine signal might be an error or misidentified sulfur dioxide. Others proposed exotic chemical reactions involving unknown minerals in Venus's atmosphere. But follow-up observations only deepened the mystery. The phosphine persisted, appearing in patches exactly where some models predicted microbial life might congregate. What makes this discovery so electrifying isn't just the what if of alien life, it's the audacity of the universe to taunt us. Venus was supposed to be a dead end, a cautionary tale of runaway greenhouse effects. Now it might be the most unexpected frontier in the search for life. If microbes really are drifting in those acidic clouds, it would mean life isn't just a fluke of Earth's Goldilocks conditions, it's a fighter, capable of cropping up in the most hostile corners of the cosmos. That realization alone rewrites the playbook for where we should look next: Europa's icy ocean, Mars's subsurface lakes, or maybe, just maybe, the choking skies of a planet we thought we'd already crossed off the list. The phosphine saga isn't over. New missions like NASA Da Vinci and the privately funded Venus Life Finder are gearing up to probe those clouds directly, hunting for more clues. But here's the kicker: even if this turns out to be a false alarm, it's already changed the game, because for the first time in decades, we're looking at Venus not as a scorched wasteland, but as a world that might still hold secrets. And in science, sometimes the most revolutionary thing isn't the answer, it's learning to ask the right questions. For decades, astronomers assumed fast radio bursts were cosmic one-hit wonders, brief blasts of energy so powerful they outshine entire galaxies, then vanish without a trace. That changed in 2016 when researchers made an electrifying discovery. Some of these bursts weren't just random flashes, they were repeating. Not in predictable rhythms, not in neat intervals, but in erratic, unpredictable patterns that defied every explanation we'd concocted. Picture a burglar alarm going off in deep space, sometimes silent for months, other times firing off multiple bursts in a single hour, and you've captured the maddening allure of repeating FRBs. The most famous of these, FRB 12112, first appeared in 2012 near a dwarf galaxy 3 billion light-years away. At first, it seemed like just another blip in the data. Then it erupted again and again. Over time, scientists cataloged hundreds of bursts from this single source, each lasting mere milliseconds but packing more energy than the Sun emits in 80 years. The leading theory: magnetars, highly magnetized neutron stars spinning so fast their magnetic fields twist into knots, triggering apocalyptic stellar quakes. But here's the catch: not all repeating bursts match magnetar behavior. Some exhibit bizarre substructures, microsecond spikes within bursts, like cosmic stutters, that suggest something far more complex. Then came the plot twist. In 2020, astronomers detected an FRB inside our own galaxy, linked definitively to a known magnetar. Case closed, not quite. While this proved magnetars could produce some FRBs, the distant repeaters still don't fit neatly into the model. Their energies vary wildly, their locations sometimes in calm galactic suburbs, other times near violent star-forming regions hint at multiple origins. And then there's the elephant in the room: could any of these patterns be artificial? When the Chinese Fast Telescope detected a repeater in 2019, with a shockingly precise 16-day cycle active for 4 days, silent for 12. Even sober scientists admitted it resembled something you'd expect from a powered source. What makes these mysterious signals so revolutionary isn't just their existence, it's what they are doing to the fabric of space itself. As FRBs travel billions of light years, they interact with the sparse particles between galaxies, leaving subtle fingerprints that let us map the universe's hidden scaffolding. Each burst is a cosmic probe, revealing the distribution of matter we could never see otherwise, and if we ever decipher their true origins, that knowledge could rewrite our understanding of extreme physics, proving the universe has energy factories beyond anything we've dreamed up. Whether they're natural or otherwise, one thing's clear: repeating FRBs are the universe's most tantalizing Morse code, and we're only beginning to crack the cipher. For centuries, the moon's sunlit face was thought to be bone dry, a dusty wasteland where any trace of water would instantly vaporize under the relentless solar glare. That assumption shattered in 2020 when NASA's SOFIA mission did the impossible. It spotted water molecules clinging to sun-bathed lunar soil. Not buried in shadowy craters, not locked away as ice, but right out in the open where no one expected them to survive. The discovery sent ripples through the scientific community because it shouldn't have been possible. Sunlight breaks water apart in mere hours, yet here it was, defying the laws of chemistry in plain sight. How does this lunar water persist? The answer lies in the moon's bizarre surface. SOFIA data revealed water molecules trapped inside tiny glass beads formed by micrometeorite impacts, miniature time capsules sealing moisture away from the sun's destructive rays. Picture a sponge made of molten glass, each microscopic pore cradling a few precious water molecules. These beads are scattered across the lunar surface, creating a hidden reservoir that could total billions of gallons. But the real breakthrough wasn't just finding the water, it was realizing how accessible it might be. Unlike ice buried in permanently shadowed craters, this water exists in sunlit regions we could easily reach with rovers or even astronauts. The implications are staggering. Water isn't just for drinking, it's the key to survival beyond Earth. Split it into hydrogen and oxygen, and you've got rocket fuel. Combine it with lunar soil, and you can grow plants. Suddenly, the moon transforms from a barren pit stop into a cosmic gas station, a stepping stone for missions to Mars and beyond. NASA Artemis program is already racing to capitalize on this discovery, planning bases near the moon's south pole where sunlight and shadow collide. Harvesting this water could slash mission costs by billions, allowing us to refuel in orbit instead of hauling every drop from Earth. Yet mysteries remain. Where did this water come from? Solar wind, ancient comet impacts, or is it proof of a far wetter lunar past, locked away in these glassy vaults? Every answer raises new questions, and that's the beauty of this discovery. It's not just about water, it's about rewriting the moon's story, revealing a world far more dynamic and resource-rich than we ever imagined. As we gear up to return, one thing's clear: the moon isn't just a destination anymore. It's a home waiting to be unlocked, and the key might be hiding in plain sight. In the constellation Cygnus, about 1,500 light-years away, a star named K84628552, better known as Tabby's star, is doing something astronomers can't explain. It flickers, not in the gentle rhythm of a planet passing by, but in violent, unpredictable dips that sometimes blot out over 20% of its light. Imagine a candle flame wavering in a draft, except this candle is a massive sun, and the draft is something we still can't identify. When astronomer Tabitha Boyajian first spotted this bizarre behavior in data from NASA Kepler telescope, the internet erupted with speculation. Could this be evidence of an alien megastructure, a so-called Dyson Sphere harnessing the star's energy? The numbers alone make Tabby's star an outlier. Most stars exhibit tiny, regular dips in brightness when planets transit them, usually by less than 1%. Tabby's star, though, plunges into darkness for days or weeks at a time, with no discernible pattern. Early theories suggested a swarm of comets might be blocking its light, but the sheer scale required thousands of giant comets orbiting in perfect unison stretches credibility to the breaking point. Then came the observations from the infrared spectrum. If comets were the culprit, their dust should glow with heat, but Tabby's star showed no such excess. The dimming, it seemed, was caused by something cold, vast, and utterly opaque. That's where the Dyson Sphere hypothesis comes in. Proposed by physicist Freeman Dyson in the 1960s, the idea was theoretical. An advanced civilization might build a colossal swarm of solar collectors around its star to capture energy. While the concept was pure speculation, Tabby's star's behavior eerily matches what such a structure might look like: sporadic, dimming as sections of the swarm drift across the star's face. Even skeptics admit it's a tantalizing thought experiment. Could we be witnessing the first evidence of intelligence operating on a cosmic scale? The truth, as always, is probably stranger than fiction. Recent studies suggest another possibility: a mangled planet, a world torn apart by gravitational forces, could create a chaotic debris field, casting irregular shadows as it orbits. Or perhaps the star itself is devouring a moon-sized object, belching out dust clouds in fits and starts. Whatever the explanation, Tabby's star has become a beacon for SETI researchers. The Breakthrough Listen project trained its radio telescopes on the star for months, hunting for artificial signals buried in the noise. So far, silence. But the absence of evidence isn't evidence of absence, just a reminder that the universe loves a good mystery. Here's why this discovery matters. Whether it's aliens, rogue planets, or some astrophysical phenomenon we've yet to name, Tabby's star forces us to confront the limits of our knowledge. It's a cosmic Rorschach test, revealing just how quick we are to project our hopes onto the unknown. Every flicker, every anomaly is a lesson in humility, proof that the universe still has cards up its sleeve. And as new telescopes like the James Webb Space Telescope turn their gaze toward Cygnus, one thing's certain: the final chapter of this mystery is far from written. Most meteors that streak through Earth's atmosphere are homegrown debris from asteroids or comets within our solar system. But in 2014, a tiny fireball blazing over the Pacific Ocean turned out to be anything but ordinary. Catalogued as Cenios 2014-008, this meteor wasn't just fast, it was interstellar, a visitor from another star system entirely. Harvard astrophysicists Amir Suraj and Avi Loeb made the stunning announcement in 2019 after analyzing its trajectory. The numbers were undeniable. This object had been hurtling through space at nearly 37 miles per second, so fast that the sun's gravity couldn't possibly have snagged it into an orbit. The implications were staggering. While Oumuamua grabbed headlines as the first known interstellar object, Cenios 2014-008 actually predated it by 3 years, making it the first recorded visitor from beyond our solar system. But unlike Oumuamua, which sailed past us untouched, this meteor did something extraordinary. It crashed, tiny fragments possibly no larger than grains of sand, likely scattered across the ocean floor near Papua New Guinea. That's where the story gets even wilder. In 2023, Suraj and Loeb led an expedition to dredge up those remnants using powerful magnets, hoping to find microscopic clues about its origins. Why go to such lengths for specks of cosmic dust? Because these fragments could carry chemical signatures unlike anything in our solar system, isotope ratios, or crystalline structures that reveal the conditions of their birth around a distant star. Some theories suggest they might even contain materials forged in a supernova or the heart of an alien protoplanetary disk. The team's initial findings: microscopic spherules with bizarre compositions, some enriched in beryllium, lanthanum, and uranium, in patterns that defy known astrophysical processes. Critics argue these could be contamination from earthly pollution or volcanic ash, but the hunt continues. What makes this discovery so revolutionary isn't just the meteor's origin, it's the door it opens. If we can confirm these fragments are interstellar, we're holding pieces of another star system in our hands. That's like receiving a cosmic message in a bottle, written in the language of atomic nuclei. Future missions could target similar meteors, building a catalog of alien geology without ever leaving Earth, and if those fragments hint at something more like artificial alloys or engineered materials. Well, that's a conversation for another day. For now, the Pacific hides its secrets, but not for long. With each scoop of ocean sediment, we're one step closer to touching the stars. Imagine stretching a ruler across the sky so vast it would take light 3.3 billion years to travel from one end to the other. Now picture that ruler not as a straight line, but as a crescent of galaxies, an unfathomably huge structure curving through the cosmos like a smile, etched into the fabric of space itself. This is the giant arc, a formation so colossal it defies one of astronomy's most fundamental assumptions, the idea that the universe on the largest scales should look roughly the same no matter where you're standing. Discovered in 2021 by astronomer Alexia Lopez while mapping distant quasars, the giant arc isn't just big, it's problematically big. According to the cosmological principle, matter should be distributed evenly across the universe once you zoom out far enough, like froth in a well-mixed latte. But the arc is a string of galaxies, galaxy clusters, and intergalactic gas spanning 1/15 the observable universe, throws that idea into question. Finding such a structure is like spotting a face in the clouds, except this face is made of 100,000 galaxies, and it shouldn't be there. What makes the arc so revolutionary isn't just its size, but its timing. The universe hasn't existed long enough for gravity to pull matter into clumps this enormous, at least according to our current models. Simulations suggest structures larger than 1.2 billion light-years couldn't form in 13.8 billion years without breaking the rules of cosmic evolution. Yet here it is, dangling in the northern sky like a challenge scribbled in starlight. Some theorists argue it might be a statistical fluke, an illusion created by overlapping smaller structures. Others whisper about exotic possibilities. Could it be a fossil imprint from the universe's inflationary infancy, a scar left by processes we don't yet understand? Then there's the eerie coincidence. The giant arc isn't alone. It joins a rogues gallery of mammoth structures, the Sloan Great Wall, the Hercules Corona Borealis Great Wall, each pushing the limits of what cosmology says is possible. Together they hint at a universe far lumpier than we thought, where matter clumps in ways that defy gravity's stopwatch. If these structures are real, they could force us to rewrite textbooks, tweaking the density of dark matter, or even revising our understanding of inflation itself. For now, the giant arc remains a tantalizing maybe. Confirming its existence requires more data, more telescopes, and more sleepless nights for theorists. But whether it's a cosmic error or a paradigm-shifting truth, one thing's clear: the universe loves to keep us guessing. Just when we think we've mapped the dance of the galaxies, it throws in a move so bold, so unexpected, it leaves us stumbling to catch up. And that's the beauty of discoveries like this. They don't just challenge what we know, they remind us how much wonder still waits, undiscovered, in the dark. Beneath the rusty surface of Mars, buried under layers of ice and dust, something extraordinary might be lurking, not just water, but entire lakes of it, shimmering in liquid defiance of the planet's frigid conditions. In 2018, the European Space Agency's Mars Express orbiter made a revelation that sent shockwaves through the scientific community. Radar signals bouncing back from the red planet's south pole showed a bright, unmistakable reflection, the kind you'd only get from a large body of liquid water. Stretching nearly 12 miles across and hidden a mile beneath the ice, this wasn't just a damp patch or a trickle, it was a subsurface lake, the first ever detected on another world. But how could liquid water exist in a place where surface temperatures average -80 degrees Fahrenheit? The answer lies in a cocktail of extreme conditions. Mars' polar ice caps are laced with salt superchlorates and chlorides that act like antifreeze, lowering water's freezing point dramatically. Combine that with the crushing pressure of overlying ice, and you've got a recipe for pockets of briny sludge that refuse to solidify. Then there's the heat. While Mars lacks volcanic activity today, residual geothermal warmth from its core, or even the insulating effect of thick ice sheets, could provide just enough energy to keep these reservoirs from freezing solid. The discovery raised an electrifying question: could these hidden lakes harbor life on Earth? Similar environments like Antarctica's Lake Vostok, sealed under 2 miles of icy teem with microbial extremophiles. If life can cling to existence in such punishing conditions here, why not on Mars? The idea isn't far-fetched. These subsurface lakes could be time capsules, preserving organisms that thrived billions of years ago when Mars had rivers and oceans. Or they might host entirely new forms of life, adapted to the dark, salty depths. Not everyone's convinced, though. Skeptics argue the radar signals could be explained by layers of clay or other minerals, not liquid water. Others point out that the salt concentrations needed to keep water liquid at these temperatures might be too extreme for even the hardiest microbes. Then there's the puzzle of energy. Without sunlight, any potential organisms would need to rely on chemical reactions, like those seen in Earth's deep-sea hydrothermal vents, to survive. But where would those chemicals come from on a geologically quiet Mars? The debate took another twist in 2021, when follow-up studies claimed to find not just one lake, but an entire network of them, interconnected like subterranean ponds. If true, this would suggest liquid water isn't a rare fluke on Mars, it's a persistent feature hiding in plain sight. NASA's upcoming Mars Life Explorer mission aims to settle the argument, designed to drill into the ice and analyze samples directly. Until then, these hidden lakes remain one of the most tantalizing mysteries in planetary science. What makes this discovery so transformative isn't just the water itself, it's the radical shift in how we view Mars. No longer just a dry, dead world, it's a planet with secrets tucked beneath its surface, waiting to be uncovered. Whether these lakes are sterile brines or thriving ecosystems, they rewrite the story of Mars from a footnote in cosmic history to a potential haven for life. And that changes everything, because if life can exist there, huddled in the dark beneath a frozen wasteland, where else might it be hiding? The universe suddenly feels a lot more crowded. Galaxies are supposed to follow certain cosmic rules, spiraling arms anchored by dark matter, an invisible scaffolding that makes up over 80% of their mass. But in 2021, astronomers stumbled upon a cosmic rebel that tossed the rulebook out the window, AGC 114905, a galaxy so empty it shouldn't exist. This faint, unassuming smudge of stars drifting in the Pisces constellation has almost no dark matter at all, a discovery so baffling it's forcing scientists to question everything they thought they knew about how galaxies form. Most galaxies behave like celestial marionettes, their visible stars and gas puppeteered by the gravitational pull of unseen dark matter. Take the Milky Way without its halo of dark matter, our galaxy would fly apart, its stars scattering into the void. That's why AGC 114905 is such an enigma. When researchers measured the speed of its stars, expecting to calculate the dark matter holding them together, the numbers came back nearly flat. The stars were moving exactly as they should if there was nothing but visible matter tugging on them. It's like finding a car speeding down the highway with no engine, just momentum and thin air. Theories immediately collided. Could the dark matter have been stripped away by a violent encounter with another galaxy? Maybe, but there's no evidence of a cosmic collision in the galaxy's structure. Others suggested the dark matter might be hiding in a state our instruments can't detect, but even that stretches current physics. The most radical idea: that AGC 114905 never had dark matter to begin with. forming instead from a rare pocket of primordial gas that somehow avoided the dark matter's scaffolding, threading the rest of the universe. What makes this galaxy so revolutionary isn't just its defiance, it's the domino effect it triggers. If dark matter isn't essential for galaxy formation, entire chapters of astrophysics need rewriting. Alternative theories like modified Newtonian dynamics, which tweak the laws of gravity to eliminate the need for dark matter, suddenly gain traction. Even more intriguing, AGC 114905 isn't alone. A handful of other dark matter-free galaxies have since been identified, suggesting this might be a rare but real cosmic phenomenon. Yet the mystery deepens with every observation. Some researchers argue we might be misreading the data, that the galaxy's odd angle or faint signals could skew measurements. Others counter that the evidence is too consistent to dismiss. The truth might lie in the shadows, waiting for next-generation telescopes like the Vera Rubin Observatory to unveil it. Until then, AGC 114905 stands as a cosmic thorn in the side of established science, a quiet reminder that the universe always has another surprise up its sleeve. Here's why this matters. Dark matter isn't just some abstract puzzle, it's the glue holding the cosmos together. If galaxies can exist without it, we're missing a fundamental piece of how the universe works. Every time we think we've got the rules figured out, the cosmos throws us a curveball, and that's exactly why discoveries like this are so thrilling. They don't just fill gaps in our knowledge, they tear them wide open, revealing how much we still have left to learn. Black holes don't just swallow light, they bend it, twist it, and sometimes, if you listen closely, they sing. In 2022, scientists detected something extraordinary from a black hole 3.9 billion light-years away, an echo. Not a sound, of course, space is silent, but a flickering pattern of X-rays bouncing off the swirling maelstrom of gas and dust known as the accretion disk. This wasn't just cosmic feedback, it was a direct snapshot of spacetime itself warping under unimaginable gravity, confirming a prediction Einstein made over a century ago in ways we'd never seen before. The discovery came from a black hole system called Zwicky 1, where a star unfortunate enough to orbit too close was being slowly torn apart. As debris spiraled into the black hole, it heated up to millions of degrees, blasting out X-rays like a cosmic strobe light. Normally, those X-rays vanish into the void, but researchers notice something peculiar: delayed flashes, arriving milliseconds to seconds after the initial bursts, like a distorted reflection. These were the echoes, created when X-rays ricocheted off the inner edge of the accretion disk, warped by the black hole's spin before escaping into space. What makes these echoes revolutionary isn't just their existence, it's what they reveal about the chaos near the event horizon. By mapping the timing and energy shifts of the reflected X-rays, astronomers could reconstruct the shape of the accretion disk in ways previously impossible. The results were startling. The disk wasn't flat, like a vinyl record, it was twisted, warped like a vinyl record left too close to a flame, its inner regions tilted by the black hole's gravitational vortex. This matched Einstein's general relativity equations with eerie precision, showing spacetime doesn't just bend, it churns, folds, and distorts in ways that defy intuition. But the real surprise came when the team compared echoes from different black holes. Some disks warped more than others, hinting at hidden variations in spin speed or magnetic field strength. One theory suggests that extreme spin might drag spacetime around it like honey on a spoon, twisting the inner disk until it nearly breaks. Others propose violent magnetic storms could fling particles outward, stirring the disk into chaos. Whatever the cause, these echoes are more than just cosmic curiosities, they're tools. By studying them, we can measure black hole spins, map the geometry of their gravitational wells, even test whether Einstein's theories hold up under conditions no lab could ever replicate. Yet mysteries remain. Why do some black holes echo while others stay silent? Could these reflections reveal hints of quantum gravity, the elusive link between relativity and the subatomic world. Every flicker brings new questions, and that's the beauty of this discovery. It's not just about proving Einstein right, it's about peering into the darkness and realizing the universe still has rhythms we're only beginning to hear. The next time a black hole sings, we'll be listening closer than ever. The Milky Way isn't just a static spiral of stars, it's a living, breathing ecosystem, and astronomers have just uncovered one of its most dramatic hidden rhythms. Picture this, a titanic fountain of gas, towering over our galaxy, spewing matter out into the void only to pull it back in again in an endless cosmic loop. This isn't science fiction, it's the reality revealed by radio telescopes in 2019 when they mapped a structure so vast it defies imagination. Stretching tens of thousands of light years above and below the galactic plane, this fountain cycles the equivalent of 100 suns worth of material every year, reshaping how we think galaxies live and evolve. For decades, scientists assumed gas ejected from galaxies was lost forever, blown away by supernova explosions or fierce stellar winds, but the Milky Way's fountain flips that idea on its head. Here's how it works: stars near the galactic center, especially massive, short-lived ones, die in violent explosions, heating surrounding gas to millions of degrees and blasting it outward at supersonic speeds. This scorching plasma surges upward like water from a geyser, reaching altitudes where it cools, condenses, and eventually rains back down in eerie, slow-motion arcs. The result? A self-sustaining recycling system where expelled gas returns to fuel new generations of stars, a process we never knew existed at this scale. What makes this discovery so groundbreaking isn't just the fountain size, it's the implications for galactic survival. Every galaxy faces a looming crisis. Star formation consumes gas, and without replenishment, galaxies would eventually burn out. The fountain solves part of that mystery, showing how galaxies like ours might hoard material instead of bleeding it into space, but the plot thickens when you consider the broader picture. Similar structures, dubbed galactic chimneys, have been spotted in other galaxies, suggesting this isn't unique to the Milky Way. It might be a universal survival tactic, a way for galaxies to cheat entropy by catching their own exhaust. Yet puzzles remain. What triggers the gas to fall back instead of escaping forever? Why do some galaxies show evidence of fountains, while others seem to hemorrhage material uncontrollably? The answers might lie in dark matter, whose gravitational embrace could act like an invisible net, gently guiding stray gas back home, or perhaps magnetic fields weaving through the galactic halo play a role in corralling the outflow. Every new observation adds another piece to the puzzle, revealing a galaxy far more dynamic than the serene pinwheel we see in photographs. This isn't just about gas and gravity, it's about redefining what it means to be a galaxy. We're not isolated islands of stars but participants in a grand, self-regulating dance, where death fuels birth and expulsion leads to renewal. The Milky Way's fountain isn't just a curiosity, it's a clue to how galaxies endure across billions of years, and possibly how our own cosmic neighborhood might weather the eons ahead. And that changes everything, because if galaxies can recycle, adapt, and sustain themselves in ways we're only beginning to understand, the universe might be far more resilient than we ever dreamed. Some planets shouldn't exist, at least not according to everything we thought we knew about how worlds form. Enter the cotton candy exoplanets, a class of worlds so light, so ethereal, they seem to defy the laws of physics. Imagine a planet the size of Jupiter, but with less than 1% of its mass, so fluffy you could practically poke a finger through its atmosphere. Scientists call them super puffs, and their existence is turning planetary formation models upside down. The first of these bizarre worlds, Kepler 51b and its siblings, were spotted in 2012 by NASA Kepler telescope. At first glance, their size suggested gas giants, but their densities told a different story. These planets are lighter than styrofoam, with atmospheres so bloated they'd float in water if you could find a bathtub big enough. The mystery: how do such fragile worlds survive the brutal radiation of their host stars without evaporating into space? One leading theory points to youth. These planets might be cosmic toddlers, barely a few 100 million years old, still swaddled in the thick shrouds of gas they were born with. Over time, stellar winds could strip away their puffy atmospheres, leaving behind denser cores, meaning we might be catching them in a fleeting phase of planetary evolution. But there's a catch: some superpuffs orbit stars billions of years older than the Sun, making their delicate structures even harder to explain. Then there's the question of composition. Normal gas giants like Jupiter are mostly hydrogen and helium, but cotton candy planets might be packed with heavier molecules: methane, carbon dioxide, or even water vapor, trapping heat and puffing up like a cosmic soufflé. Others speculate their extreme low density comes from colossal rings or vast, dusty debris fields stretching far beyond the planets themselves, creating the illusion of a gargantuan atmosphere. The real shocker: these worlds might be more common than we thought. Recent surveys suggest up to 15% of exoplanets could fall into the super puff category, hiding in plain sight because their wispy nature makes them harder to detect. If that's true, our understanding of planet formation is missing a crucial piece, one where gas, dust, and stellar winds interact in ways we've yet to model. What makes these planets revolutionary isn't just their strangeness, it's the doors they open. If cotton candy worlds can exist, what other outliers are waiting to be found? Could there be planets with densities so low they're practically invisible? Or when so old they've somehow defied evaporation against all odds? Every new discovery peels back another layer of the cosmic rulebook, reminding us that the universe loves to break its own rules. And that's the thrill of the hunt, because the moment we think we've got it all figured out, the cosmos tosses us another mystery, wrapped in a package as light as a whisper. For decades, the universe had a glaring accounting problem. Nearly half of its ordinary matter was missing. Not dark matter, not some exotic substance, but the regular protons, neutrons, and electrons that make up everything we can see. Scientists called it the missing baryon problem, and it was one of cosmology's most embarrassing gaps. If our models were right, about 50% of the universe's expected normal matter had simply vanished without a trace. Then in 2018, astronomers finally cracked the case, and the answer was hiding in plain sight, woven between galaxies and threads of gas so faint they'd been all but invisible. The breakthrough came not from peering at stars or planets, but from studying the empty spaces between them. Researchers had long suspected the missing matter might be lurking in vast, diffuse filaments of warm, hot intergalactic medium, WIM for short. Picture these as cosmic spiderwebs, stretching millions of light-years between galaxy clusters, their strands so tenuous a single cubic meter might hold just a handful of atoms. Spotting something that thin is like trying to see a flashlight beam in a foggy forest at midnight, but scientists found a clever workaround. They used the light of distant quasars as cosmic flashlights. As quasar light travels through space, it gets subtly absorbed by any matter in its path, leaving faint chemical fingerprints in its spectrum. By analyzing thousands of these absorption lines, teams working with the European Space Agency's XMM Newton telescope and NASA Chandra X-ray Observatory finally detected the telltale signatures of oxygen ions, evidence of the WIM presence. The numbers added up perfectly. When they tallied all these wispy filaments, they accounted for every last bit of the universe's missing matter. But here's where it gets even more fascinating. These filaments aren't just floating idly, they're part of an intricate cosmic circulatory system. Supercomputer simulations show them funneling gas into galaxies, fueling star formation, and recycling material ejected by supernova back into the intergalactic medium. They're the universe's hidden plumbing, connecting galaxies in a web far more vast than anything we'd imagined. Some researchers now believe these filaments might even guide the growth of galaxy clusters, acting like invisible highways for matter in an otherwise empty void. Yet mysteries linger. Why is this gas so hot? Some strands reach temperatures of millions of degrees, likely heated by shock waves from colliding galaxy clusters or energy pouring out of active black holes. And how does something so diffuse stay cohesive over cosmic distances? Magnetic fields might play a role, or perhaps dark matter's gravitational pull helps corral these faint structures. Every answer peels back another layer, revealing a universe far more interconnected and far more dynamic than we ever suspected. What makes this discovery so transformative isn't just solving an old puzzle, it's rewriting how we see the cosmos. The space between galaxies isn't empty, it's a bustling network of matter, energy, and motion, pulsing with hidden activity, and that changes everything. Because if we've been overlooking something as fundamental as half the universe's ordinary material, what else might we still be missing? The search isn't over, it's just begun. Imagine staring into the heavens and seeing not just stars, but the invisible forces pulling them apart, the fingerprints of dark energy etched across the cosmos. That's exactly what the dark energy camera accomplished when it began mapping the universe in breathtaking detail. Perched atop a mountain in Chile, this 600-megapixel behemoth spent years photographing galaxies so distant their light had traveled for billions of years before reaching its lenses. But this wasn't just a cosmic photo album. Every image held clues to the universe's most perplexing secret: why is everything accelerating away from everything else? The camera's mission was simple in concept but revolutionary in execution. By cataloging the positions and shapes of over 300 million galaxies, it created the most precise three-dimensional map of the universe ever made. Here's how it worked. As light from faraway galaxies passes through the cosmos, it gets subtly distorted by the gravitational pull of dark matter, the universe's invisible scaffolding. The camera's ultra-sensitive detectors could measure these distortions, revealing where dark matter lurked, but the real surprise came when scientists combined this data with measurements of supernova. The results confirmed dark energy wasn't just a placeholder in equations, it was real, pervasive, and growing stronger over time, stretching the fabric of space itself. Yet for every answer, the camera unveiled new mysteries. Why does dark energy's strength match the critical density needed for a flat universe so perfectly? It's like finding a dial set exactly to zero against astronomical odds. Even stranger, some regions of space appear to be accelerating faster than our models predict, as if dark energy isn't uniform but clumpy, a possibility that defies everything we thought we knew. Then there's the Hubble tension, where different methods of measuring cosmic expansion disagree by just enough to keep astronomers awake at night. The camera's data deepened this rift, suggesting our understanding of the universe's timeline might be missing a crucial chapter. The most haunting revelation: dark energy seems to be winning its tug of war with gravity. If this continues, distant galaxies will one day vanish beyond an unreachable horizon, leaving future civilizations with a night sky nearly empty of stars. But here's the twist: the camera also captured evidence of colossal voids, regions of space so empty they might be counteracting dark energy's push, creating a cosmic ballet we're only beginning to fathom. What makes this discovery monumental isn't just confirming dark energy exists, it's realizing how little we grasp its nature. Is it the energy of empty space? A new force field, or something beyond physics as we know it? The dark energy camera didn't just map galaxies, it handed us a mirror, reflecting how much of the universe remains hidden in plain sight. And that's the thrill of the hunt. Every pinpoint of light in its images isn't just a galaxy, it's a question, waiting for its answer to unravel the cosmos. For nearly a century, neutrinos have been the universe's most elusive ghost subatomic particles, so indifferent to matter they could pass through a light year of lead without a single collision. Billions stream through your body every second, leaving no trace. Yet in 2017, scientists achieved the impossible. They caught one of these phantoms red-handed, not just detecting it but tracing its origin 4 billion light-years across the cosmos to a monster known as a blazar. This wasn't just another neutrino sighting, it was the smoking gun linking these enigmatic particles to one of the most violent phenomena in existence, and it opened an entirely new window onto the universe. The saga began when an alert blared from the Ice Cube Neutrino Observatory, a detector buried deep in Antarctic ice. A single neutrino, carrying unprecedented energy about 300 times that of protons in the Large Hadron Collider, had slammed into an ice molecule, creating a faint blue flash sensors couldn't ignore. Within seconds, observatories worldwide swiveled toward the neutrino's rough path. There, in the constellation Orion, sat TX 0506 plus 056, a blazar, a supermassive black hole at the heart of a galaxy, spewing a jet of plasma directly at Earth. As telescopes analyzed its light, the pieces fit. Gamma rays from the blazar flared at the exact moment the neutrino arrived, betraying its birthplace. Why is this so revolutionary? For starters, it confirmed what theorists had long suspected. Blazars aren't just cosmic particle accelerators, they're neutrino factories. Their jets, powered by black holes spinning at nearly light speed, can hurl particles across the universe with energies dwarfing anything humans could ever create. But more importantly, this marked the dawn of multi-messenger astronomy, where we don't just study light but combine it with signals like neutrinos and gravitational waves to see the cosmos in ways previously unimaginable. It's like upgrading from silent films to surround sound suddenly. The universe is speaking to us in multiple languages at once. The implications ripple far beyond one detection. Neutrinos, unlike light, travel unimpeded through dust, gas, and even entire galaxies, carrying pristine information from their sources. By tracking them, we could map the universe's most hidden corners, regions obscured by cosmic fog or drowned out by brighter signals. Already, follow-up studies suggest other blazars might be neutrino emitters, hinting at a vast, invisible network of particle accelerators threading the cosmos. Some researchers even speculate these particles could carry clues about dark matter or reveal processes so extreme they defy known physics, yet mysteries linger. Why do only some blazars produce detectable neutrinos? What exact mechanism in those jets cranks particles up to such insane energies? Every unanswered question is a reminder that this discovery isn't an endpoint, it's a roadmap. With upgrades to IceCube and new detectors on the horizon, we're on the verge of turning neutrino astronomy into a routine tool, peeling back layers of the universe we've never seen before. The ghosts are talking, and this time we're listening. Luke Skywalker's home planet of Tatooine from Star Wars had 2 suns, but the real universe just showed us something even more spectacular. Meet LTD 1445 ABCB, an exoplanet locked in a gravitational dance with not 2, but 3 stars, discovered in 2021 by NASA TESS telescope. This world defies everything we thought we knew about how planetary systems form and survive. Imagine standing on its surface. One moment, triple sunrises paint the sky in molten hues. The next, darkness falls as the stars eclipse each other in an endless celestial waltz. The sheer chaos of this arrangement shouldn't work, yet there it is, a planet thriving where by all rights none should exist. What makes this system so mind-bending is the physics at play. Most planets orbit a single star, with stable, predictable paths. Binary star systems, while rare, can still host planets if they're close enough to one star or orbit both at a safe distance. But 3 stars, that's a gravitational minefield. LTD 1445 AB orbits the primary star in the system, while 2 smaller stars twirl around each other farther out, creating a volatile environment where tidal forces could easily shred a planet to pieces. Yet somehow this world clings to stability, a testament to cosmic fine-tuning we're only beginning to understand. The planet itself is a marvel, roughly 7 times Earth's mass, it's likely a gas dwarf or mini-Neptune, blanketed in thick atmospheres that might glow under the relentless light of its stellar trio. Temperatures on its sun-facing side could exceed 700 degrees Fahrenheit, while the night side, constantly shifting due to the star's complex orbits, might experience wild temperature swings. But here's the real kicker. Simulations suggest the two outer stars' gravitational tugs would regularly yank the planet's orbit out of round, stretching it into an oval before snapping it back. That means seasons, if you could call them, that wouldn't just change gradually, they'd flip like a switch, plunging the world between extremes with no warning. Astronomers are obsessed with systems like this because they're cosmic stress tests, pushing the limits of what's possible. If a planet can survive here, it forces us to rethink the rules. Maybe planetary formation is more resilient than we thought, with worlds assembling in pockets of calm amid stellar chaos, or perhaps LTT 1445 ABCB migrated inward after forming in a quieter outer region, dodging destruction through sheer luck. Every scenario challenges textbook models, proving the universe has a flair for the dramatic. The most thrilling part, this isn't a one-off. Other triple-star planets like Kelt 4 ABCB and GW Orionis's potential world hint that such systems might be more common than we ever imagined. Each one is a laboratory for studying gravitational physics, planetary climates, and even the potential for life in unthinkable conditions, because if a planet can find stability amid 3 suns, what other impossible worlds might be waiting in the dark? The answer could rewrite not just astronomy, but our place in the cosmos. After all, if there's room for a planet like this, the universe might be far stranger and far more generous than we dared to dream. One of the universe's most terrifying forces just broke free, and it's dragging a cosmic crime scene behind it. In 2023, the Hubble Space Telescope captured something no one expected, a supermassive black hole weighing as much as 20 million suns, barreling through interstellar space at breakneck speed. But this wasn't just any rogue object. Stretching behind it like a celestial wake, a 200,000 light-year-long trail of young, blazing stars shone with eerie brilliance, as if the black hole had carved a river of starlight through the void. Astronomers had stumbled upon something unprecedented, a runaway black hole, fleeing the scene of an ancient galactic collision, with evidence literally glowing in its wake. The story begins with a cataclysmic merger. Most galaxies host central black holes, and when two galaxies collide, their black holes eventually spiral together, locked in a gravitational dance. Normally they'd merge into one, but this time something went violently wrong, as 3 galaxies smashed together 2 large galaxies and a smaller third. Their central black holes engaged in a chaotic tango. The smallest one got too close, and the larger pair slingshotted it into oblivion, flinging it outward at speeds exceeding 4 million miles per hour. The force of the ejection was so extreme, it ripped through the galaxy's gas clouds, compressing and superheating them until they ignited into a chain of newborn stars. Picture a cosmic plow tearing through a field, leaving a furrow of fire in its path. What makes this discovery so startling isn't just the black hole's escape, it's the stars it left behind. These aren't ordinary stars, they're packed densely along the trail like cosmic breadcrumbs, some no more than a few million years old, glowing blue with youthful intensity. Normally, star formation requires the gentle collapse of gas clouds over eons. Here, the black hole's chaotic exit triggered a shockwave of creation, turning destruction into genesis. It's a paradox that rewrites our understanding of how stars can form, not in quiet nurseries, but in the wreckage of gravitational violence. The implications ripple far beyond this one event. If supermassive black holes can be ejected from their galaxies, how many others are drifting unseen in the darkness? Some theories suggest these rogue behemoths might lurk in the voids between galaxies, invisible except for the faint glow of any stars they've kidnapped along the way. Others propose they could seed new galaxies, their stolen gas eventually coalescing into fresh stellar systems. even more haunting, if this black hole's trajectory holds, it may never stop, destined to wander the cosmos forever, a ghost of the collision that spawned it. Yet the biggest question remains unanswered: what happened to the other two black holes in this cosmic showdown? Did they merge as expected, or was the recoil so violent they too were sent careening in opposite directions? Future telescopes like the Nancy Grace Roman Space Telescope could hunt for their hiding places, piecing together the full story of this galactic hit and run. Until then, the runaway black hole serves as a reminder the universe doesn't just create and destroy. Sometimes it flees the scene, leaving behind a trail of evidence that glows just bright enough for us to follow. Stretching over 1.8 billion light-years across the constellation Eridanus, there's a patch of space so unsettlingly cold it shouldn't exist. Discovered in 2004 by NASA Wilkinson Microwave Anisotropy Probe, this cosmic anomaly, dubbed the cold spot, lingers in the afterglow of the Big Bang like a shadow no theory can fully explain. The cosmic microwave background, that faint echo of the universe's birth, is remarkably uniform, with tiny temperature fluctuations betraying the seeds of galaxies to come. But the cold spot is different. It's colder than its surroundings by about 70 microkelvin, a seemingly small difference, but statistically so extreme it stands out like a scream in a quiet room. And for nearly 2 decades, scientists have been locked in a fierce debate: is this the fingerprint of something beyond our universe, or proof our cosmic models are missing a critical piece? The most tantalizing explanation comes from the fringes of cosmology. Some theorists propose the cold spot might be a bruise left by a collision with another universe during the chaotic infancy of our own. According to multiverse hypotheses, other bubble universes could exist beyond ours, each with different physical laws. If one grazed ours during cosmic inflation, the explosive expansion following the Big Bang, the energy transfer could have left behind a vast, underdense region, a void where matter is unusually sparse, stretching the fabric of space and cooling the light that passes through it. Simulations show such a collision could create a cold spot-like imprint, making this one of the few testable predictions of the multiverse theory. But critics pounce on a glaring issue: if this were truly an intersection with another reality, why haven't we found more of them? Enter the skeptics with an alternative: the cold spot might be a supervoid, an immense cosmic desert where galaxies are eerily scarce. Light traveling through such a region loses energy as it climbs out of the void's gravitational well, shifting to longer, cooler wavelengths, a phenomenon called the integrated Sachs-Wolf effect. But even this explanation falters under scrutiny. Surveys mapping galaxy distributions show the cold spot isn't quite empty enough to account for the temperature drop. The void we've found is big, but not big enough, unless there's an even larger, darker structure lurking just beyond our detection, perhaps made of exotic matter or tangled in unseen magnetic fields. The math just doesn't add up. That leaves a third, more unsettling possibility. Maybe we've misunderstood inflation itself. The standard model paints inflation as a smooth, uniform process, but what if it was patchy? Tiny flaws in spacetime's early expansion could have created regions where density fluctuated wildly, leaving behind pockets like the cold spot as cosmic scars. If true, it would mean rewriting our origin story, admitting that the universe's birth was messier, more unpredictable than we thought. Some theorists are already crafting alternatives, like eternal inflation, where multiple Big Bangs occur in a never-ending fractal of universes, each with its own quirks. The cold spot, then, might be our first glimpse of deeper physics governing realities beyond our own. Yet for all the theories, the cold spot stubbornly refuses to yield its secrets. New telescopes like the Simons Observatory in Chile are scanning it with unprecedented precision, hunting for subtle polarization patterns in the microwave background that could betray a collision's shockwaves. Others are probing the void with galaxy surveys, searching for hidden structures that might tip the scales toward mundane explanations. What makes this mystery so thrilling isn't just the science, it's the stakes. If the cold spot is a window into the multiverse, it could rank among the most profound discoveries in history. If it's a flaw in inflation, it's a reminder that even our best theories are works in progress. And if it's something else entirely, well, that's the beauty of the cosmos. It always keeps one last card up its sleeve. Neutron stars are cosmic tightrope walkers balancing on the edge of oblivion, where one wrong step should plunge them into the abyss of a black hole. Theory says once these collapsed stellar cores pack more than about 2.2 solar masses into a sphere no wider than a city, gravity should win, crushing them out of existence. But in 2020, astronomers found a rebel that refuses to play by the rules, J0740 plus 6620, a neutron star so massive it shouldn't exist. Tipping the scales at roughly 2.35 times the Sun's mass, this cosmic anomaly is pushing the limits of quantum physics to their breaking point and forcing us to rethink what keeps these ultra-dense objects from collapsing. The discovery came from careful observations of a binary system nearly 4,600 light-years away, where this heavyweight neutron star orbits a white dwarf. By tracking subtle distortions in radio pulses from the neutron star, a technique called pulsar timing, researchers could precisely calculate its mass. The result sent shockwaves through astrophysics. Existing models suggested that at this mass, the neutrons at the star's core should succumb to gravity, collapsing into a singularity. Yet here it was, spinning steadily, its existence defying every textbook prediction. So how does it survive? The answer might lie in the bizarre physics of neutron star interiors. At these extreme densities, matter stops behaving like anything we know. Protons and electrons merge into a sea of neutrons, which under unimaginable pressure might dissolve further into a soup of quarks, the fundamental particles that make up protons and neutrons. Some theories suggest an even stranger phase called strange matter, where exotic particles stabilize the core against collapse. Others propose repulsive forces from quantum interactions create an invisible pressure barrier, like a microscopic force field holding back gravity's grip. But here's the twist: if these exotic states of matter exist inside J0740 plus 6620, they could rewrite our understanding of nuclear physics. Laboratories on Earth can't replicate these conditions. Our most powerful particle colliders only scratch the surface of neutron star densities. This makes these cosmic outliers the ultimate natural laboratories, offering glimpses into physics we could never study otherwise. The implications ripple far beyond astronomy. Understanding how matter behaves at these extremes could unlock secrets about the early universe, where similar conditions existed mere moments after the Big Bang. Yet mysteries abound. Why do all neutron stars this massive avoid collapse? Is there a tipping point where even these quantum defenses fail, and could there be even heavier neutron stars lurking undetected, pushing the limits further? Future telescopes like the Square Kilometre Array aim to hunt for more of these extreme objects, testing whether J0740 plus 6620 is a rare fluke or the first of a new class. What makes this discovery so thrilling isn't just the defiance of expectations, it's the reminder that the universe loves to test boundaries. Just when we think we've charted the rules of stellar evolution, a rebel star emerges, forcing us to question what we thought was impossible. And that's where the real magic happens, not in the answers we have, but in the questions we never saw coming. In late 2019, one of the night sky's most recognizable stars began behaving like a flickering light bulb, and the entire astronomy community held its breath. Betelgeuse, the fiery red shoulder of Orion, a supergiant so vast it would engulf Jupiter's orbit if placed in our solar system, was dimming at an unprecedented rate. By February 2020, it had lost over two-thirds of its usual brightness, a dramatic fade visible even to casual stargazers. The immediate assumption was terrifying and thrilling in equal measure. Was Betelgeuse about to explode? This wasn't just routine stellar variability. Betelgeuse is a pulsating star, known to brighten and dim in cycles, but nothing like this had been recorded in the century and a half since astronomers began tracking it. Panicked headlines warned of an impending supernova, a once-in-a-millennium cosmic fireworks display that could outshine the moon, but the truth, as scientists soon uncovered, was far stranger and more illuminating than anyone expected. Observations from the Hubble Space Telescope and Chile's Very Large Telescope revealed the culprit. Betelgeuse had coughed up a colossal dust cloud, a massive ejection of surface material, likely triggered by a sudden temperature drop in the star's outer layers, had condensed into microscopic grains that partially obscured its light. Imagine a bonfire suddenly buried under a heap of soot. The fire still rages, but the view from outside is dimmed, yet this wasn't just any stellar belch. The sheer scale of the event hinted at deeper turmoil. Betelgeuse's surface is a bubbling cauldron of plasma cells, each larger than Earth, and the dimming suggested one of these cells had erupted violently, flinging debris into space. What makes this discovery so gripping isn't just the spectacle, it's what it teaches us about stellar death throes. Betelgeuse is a ticking time bomb, destined to explode as a supernova within the next 100,000 years, a cosmic blink of an eye. Watching its antics now is like catching a preview of the universe's most destructive encore, and while the great dimming wasn't the prelude to that final explosion, it offered a rare glimpse into the chaotic processes that precede it. Supergiants don't fade quietly into oblivion. They thrash, convulse, and shed their skin in violent fits, and we got front row seats to one of those tantrums. But the story doesn't end there. In April 2020, Betelgeuse abruptly brightened again, dispelling the supernova fears but deepening the mystery. Why did the dust dissipate so quickly? Was this a one-time event or a sign of increasing instability? Some astronomers speculate the star's pulsations might be entering a new phase, with more dramatic dimming episodes to come. Others suggest we witnessed a fluke, a perfect storm of stellar conditions unlikely to repeat anytime soon. The real lesson here isn't just about one star's drama, it's about humility. Betelgeuse reminded us how much we still don't understand about the final stages of stellar evolution. For all our models and telescopes, nature still has surprises up its sleeve. And when Betelgeuse does finally explode, it won't just be a spectacle, it'll be a masterclass in cosmic chaos, written in light across the sky, a reminder that even the mightiest stars are fleeting, and the universe is always ready to school us in the art of wonder. Jupiter doesn't just dominate the solar system with its size, it orchestrates a symphony of cosmic proportions, and for the first time, we're able to listen in. When NASA Juno spacecraft slipped into orbit around the gas giant in 2016, its instruments picked up something extraordinary: the haunting songs of Jupiter's magnetosphere, a swirling force field so vast it could swallow the sun. These aren't sounds in the traditional sense. Space is a vacuum, after all, but radio waves emitted by charged particles trapped in Jupiter's magnetic grip, converted into frequencies our ears can perceive. The result? A chorus of eerie whistles, crackles, and pulses that sound less like a planet and more like the soundtrack of an interstellar haunted house. What makes these emissions so mesmerizing is how they dwarf Earth's own magnetic whispers. Jupiter's magnetosphere is the most powerful in the solar system, stretching millions of miles, so far that if it were visible, it'd appear larger than the full moon in our sky. Where Earth's magnetic field gently hums with the vibrations of solar wind, Jupiter's roars like a tempest, its charged particles accelerated to near light speed by the planet's crushing gravity and rapid rotation. Juno's recordings capture this chaos, bursts of plasma waves crashing like ocean waves against a shore, or sudden spikes resembling dolphin clicks, a phenomenon scientists call Jovian chorus. These sounds aren't just cosmic white noise, they're the heartbeat of a magnetic monster, pulsing with secrets about how the planet's invisible forces shape its environment. But the real magic happens when these radio waves collide with Jupiter's atmosphere, igniting auroras that put Earth's northern lights to shame. Unlike our planet, where auroras dance near the poles, Jupiter's blaze relentlessly, fueled by particles not just from the Sun, but from its volcanic moon Io, which spews sulfur dioxide into space like a cosmic geyser. Juno's cameras captured these auroras in unprecedented detail, rivers of blue and pink, swirling in patterns unlike anything seen on Earth, their intensity tied directly to the magnetosphere's music. When the chorus grows frenetic, the lights flare brighter, as if the planet itself is conducting a light show in sync with its magnetic orchestra, yet mysteries linger. Why do some frequencies resemble Earth's chorus waves, while others sound utterly alien? Could Jupiter's metallic hydrogen core, crushed under unimaginable pressure, be vibrating in ways that amplify these signals? And what about the odd silences, gaps in the recordings where the magnetosphere falls eerily quiet, as if holding its breath? Each question peels back another layer of Jupiter's complexity, revealing a world where physics bends to extremes we're only beginning to fathom. Juno's recordings do more than dazzle, they redefine how we understand planetary magnetic fields. By comparing Jupiter's roars to Earth's whispers, scientists are uncovering universal principles about how magnetospheres protect planets, channel energy, and even influence the potential for life. Turns out the cosmos isn't just a silent void, it's a stage where planets sing in frequencies we're only now learning to hear, and Jupiter's voice, vast and haunting, might hold the keys to unlocking magnetic mysteries far beyond our solar system. Hidden in the depths of the Coma cluster, some 330 million light-years away, lurks an enigma that shouldn't exist, a galaxy so faint it's nearly invisible, yet so massive it defies logic. Meet Dragonfly 44, the phantom of the cosmos, discovered in 2016 by the Dragonfly Telephoto Array, a revolutionary telescope designed to spot ultra-dim objects. This galaxy emits barely 1% of the light expected for its size. Yet its stars move at dizzying speeds, betraying the presence of something colossal holding them together. The verdict: Dragonfly 44 is 99.99% dark matter, a shadowy behemoth with almost no ordinary atoms to call its own. How does a galaxy like this even form? Traditional models suggest galaxies grow around halos of dark matter, which act like scaffolding for gas and stars to coalesce. But Dragonfly 44 flips that script entirely. Here, the dark matter didn't just guide the galaxy's birth, it became the galaxy. Astronomers estimate it contains roughly as much dark matter as the Milky Way, but where our galaxy teems with hundreds of billions of stars, Dragonfly 44 has a meager sprinkling, about one star for every 100 in a typical galaxy. The stars it does have drift lazily, like fireflies in an endless void, their motion dictated entirely by the gravitational pull of unseen mass. Theories about its origins range from the plausible to the mind-bending. One camp argues it's a failed galaxy, a cosmic stillbirth where normal matter never properly condensed, leaving the dark matter halo naked and exposed. Another suggests it might be the remnants of a larger galaxy, stripped bare by tidal forces, its stars ripped away during violent collisions with neighboring galaxies. But the most radical idea, that Dragonfly 44 represents an entirely new class of objects, dark galaxies that formed primarily from dark matter interactions, with ordinary matter as little more than a cosmic afterthought. What makes this discovery so unsettling is what it implies about the universe's hidden architecture. If dark galaxies are common, they could solve one of cosmology's lingering puzzles, the missing satellites problem. Simulations predict our Milky Way should be surrounded by thousands of small satellite galaxies, yet we've only found a few dozen. Could the rest be made of dark matter, invisible to our telescopes? Dragonfly 44 might be the first clue in a much larger mystery, hinting at a shadow universe of dark structures interwoven with our own. Yet the biggest question remains unanswered: what exactly is dark matter doing in there? Is it clumped into exotic particles, swirling in currents we can't detect, or could it be threaded through the galaxy in vast, cosmic filaments, bending spacetime in ways we've yet to comprehend? Future observatories like the Vera Rubin telescope aim to hunt for more of these ghosts, mapping their distribution and behavior. Until then, Dragonfly 44 stands as an eerie reminder: the cosmos isn't just what we see. It's what we can't see, shaping the universe from the shadows, and every time we think we've grasped the rules, the darkness throws us another riddle. Deep in the outer reaches of our solar system, beyond the icy realm of Neptune, something massive appears to be tugging at the fabric of space itself, and the clues are piling up. Astronomers call it Planet 9, a hypothetical world up to 10 times the mass of Earth, lurking so far from the Sun it could take 15,000 years to complete a single orbit. The evidence for its existence isn't direct. No telescope has spotted it yet, but the cosmic breadcrumbs it's left behind are impossible to ignore. It all started with a peculiar pattern in the orbits of distant icy bodies. In 2014, astronomers Chad Trujillo and Scott Shepard noticed a cluster of extremal trans-Neptunian objects, small worlds like Sedna and Biden, whose elongated orbits pointed eerily in the same direction, as if sculpted by an unseen hand. Statistically, the odds of this happening by chance were less than 0.1%. Then came the clincher: these orbits were also tilted in unison, their angles defying the natural randomness of the solar system. The most plausible explanation: a massive planet's gravitational pull, herding these objects like sheep. But Planet 9's fingerprints don't stop there. Simulations show its presence could explain other solar system mysteries, like why the plane of our planets is tilted 6 degrees relative to the Sun's equator, or why some Kuiper belt objects orbit backward, against the flow of everything else. Some researchers even speculate it might be responsible for the odd, wobbly tilt of the Sun itself, as if the star is subtly off balance under the weight of a hidden companion. The hunt for this phantom planet is unlike anything in modern astronomy, because it's so distant, perhaps 600 times farther from the Sun than Earth. It reflects almost no sunlight, making it a billion times dimmer than Jupiter. To find it, teams are combing through infrared surveys with machine learning, searching for the faintest pixel drifting against the star field. Others are tracking gravitational anomalies in the paths of spacecraft like Cassini, hunting for minuscule deviations that might betray the planet's position. Yet the most tantalizing question isn't where Planet 9 is, it's what it might be. Could it be a rogue exoplanet, captured by the Sun's gravity during a close encounter with another star, a primordial super-Earth, frozen in time since the solar system's birth? Or something even stranger: every undiscovered world holds the potential to rewrite history, and this one, if it's out there, could redefine our place in the cosmic neighborhood. Until then, Planet 9 remains the ultimate celestial ghost story, a shadow at the edge of our vision, pulling strings we're only beginning to trace. And whether it's found tomorrow or in a century, the pursuit itself is a reminder our solar system still has secrets, and the most surprising ones might be hiding in plain sight. Remember Tabby's star, that bizarre flickering sun that had everyone whispering about alien megastructures? Well, buckle up, because the mystery just got deeper. New observations have peeled back another layer of this cosmic oddity, and while some answers have emerged, the bigger picture remains as tantalizingly unclear as ever. The latest data reveals something both mundane and extraordinary. The star's infamous dimming episodes aren't caused by a monolithic structure, but by vast clouds of fine dust. Sounds simple, right? Except this dust behaves like nothing we've ever seen. For years, the leading natural explanation involved swarms of comets, thousands of them, orbiting the star in tight formation, blotting out its light at irregular intervals. But detailed spectral analysis from the Lick and Keck observatories delivered a knockout punch to that theory. When comets pass in front of stars, they leave behind traces of gas, like icy fingerprints in the starlight. Tabby's star showed no such traces. Instead, the dimming came with a telltale reddening effect, the signature of particles smaller than a grain of flour, scattering shorter wavelengths of light. This wasn't comet debris, it was something far finer, far stranger, dust so tiny it shouldn't stay aloft in the star's radiation pressure without some unseen force shepherding it. Here's where things get weird. Normally, dust this fine would either spiral into the star or blow away entirely within centuries, yet Tabby's star's dimming events have persisted for over a decade, suggesting the dust is constantly replenished. Some astronomers propose a catastrophic collision between planets or moons, grinding rocky bodies into powder and leaving behind a sprawling debris field. Others wonder if the dust is trapped in orbit by an unseen planet's gravity, like Saturn's rings on a galactic scale, but the most electrifying possibility. The dust could be artificial nanoparticles deliberately engineered to harvest stellar energy, a hallmark of speculative technology known as a Dyson swarm. Before you dismiss that as sci-fi, consider this: the dust clouds around Tabby's star don't behave like natural circumstellar dust seen elsewhere in the galaxy. They're uneven, clustering in ways that defy gravitational expectations, and their particle sizes are suspiciously uniform, exactly what you'd expect if someone were optimizing them for light absorption. Even skeptics admit the data leaves room for interpretation. As astrophysicist Jason Wright put it, "We've ruled out a solid megastructure, but a fragmented one." That's still on the table, yet the story takes another twist. In 2021, Tabby's star did something unprecedented. It dimmed asymmetrically. One side of the star darkened more than the other, a phenomenon never observed in natural dust clouds, which typically obscure stars evenly. This lopsided dimming hints at structures with defined edges, perhaps vast, uneven rings or arc-like formations orbiting at breakneck speeds. Could these be megastructure fragments or just another quirk of cosmic chaos? The truth is, Tabby's star has become more than an astronomical curiosity. It's a litmus test for how we approach the unknown. Every time we think we've pinned it down, it throws us another curveball, forcing us to stretch our imaginations and question our assumptions. Whether the answer lies in exotic astrophysics or something even more extraordinary, one thing's certain: this star isn't done surprising us. And that's the real gift of mysteries like this. They don't just challenge what we know, they remind us how much wonder is left to uncover. Time crystals sound like something ripped straight from science fiction structures that pulse in a never-ending rhythm without energy input, defying one of the most fundamental laws of physics. Yet in 2021, scientists aboard the International Space Station didn't just imagine them, they created them, unlocking a quantum phenomenon so bizarre it could redefine the future of computing. Unlike everyday crystals where atoms arrange themselves in repeating spatial patterns, time crystals exhibit order in time. Picture a diamond that doesn't just sit static on a ring, but one whose atoms periodically rearrange themselves, clicking like a cosmic metronome without ever winding down. This perpetual motion doesn't violate thermodynamics because the crystals don't produce energy. They exist in a stable, self-repeating quantum state, unchanging even as the universe around them evolves. The secret lies in their construction. Researchers use lasers to nudge a chain of charged atoms ions into a fragile, entangled state where they flip back and forth between configurations indefinitely, like a flipbook animation that never runs out of pages. But here's the twist: gravity ruins everything. On Earth, even the faintest vibrations or gravitational nudges disrupt the delicate balance required to sustain time crystals. That's why the ISS became the perfect laboratory. In microgravity, shielded from terrestrial interference, scientists could extend the crystal's coherence time, observing their rhythmic cycles for far longer than ever possible on the ground. The implications are staggering. Time crystals aren't just curiosities, they could be the missing link for fault-tolerant quantum computers. Traditional quantum systems are notoriously fragile, their qubits collapsing at the slightest disturbance. But a time crystal's inherent stability, its ability to maintain coherence despite external noise, might offer a workaround, acting as a natural error correction mechanism for quantum calculations. Yet the real magic lies in how these crystals blur the line between quantum and cosmic scales. Some theorists speculate that time crystals might mimic exotic states of matter predicted to exist inside neutron stars or near black holes, where spacetime itself twists into knots. Others wonder if they could serve as prototypes for entirely new phases of matter, ones that might one day power interstellar communication networks or even cosmic-scale sensors. For now, these crystalline oddities remain confined to lab experiments and orbital stations, their rhythms ticking away in silent defiance of the universe's tendency toward chaos. But every oscillation, every flawless cycle, whispers a tantalizing promise that the boundary between impossibility and breakthrough might just be a matter of time. Cosmology is facing a crisis, one so profound it might force us to rewrite the universe's operating manual. At the heart of the turmoil is a number called the Hubble constant, which measures how fast the cosmos is expanding. For decades, scientists assumed nailing down this value would be straightforward, but the universe, it seems, enjoys a good plot twist. Two of the most trusted methods for calculating the Hubble constant now disagree by a staggering margin, and the gap, dubbed the Hubble tension, isn't just persisting. It's widening. The first method relies on the cosmic microwave background, the afterglow of the Big Bang. By analyzing subtle temperature fluctuations in this ancient light, the Planck satellite delivered a Hubble constant of about 67 kilometers per second per megaparsec. Translation: for every 3.26 million light-years you look deeper into space, galaxies appear to recede 67 kilometers per second faster. This approach is rooted in the early universe's physics, where everything was simpler, hotter, and denser. Then there's the second method, observing pulsating stars called cepheids and cataclysmic supernova in nearby galaxies. These cosmic yardsticks let astronomers measure distances and velocities directly, building a step-by-step ladder to the present-day expansion rate. Teams using Hubble Space Telescope data, including Nobel laureate Adam Rees, consistently land on a value around 73. That 6-point difference might sound trivial, but statistically, it's like flipping a coin and getting heads 20 times in a row possible, but so unlikely it screams that something's wrong. At first, researchers brushed it off as measurement errors. Maybe cepheids were trickier to calibrate than thought, or perhaps Planck's data needed tweaking. But as instruments improved, the discrepancy hardened. New techniques like using gravitational lensing of quasars or the echoes of merging neutron stars only deepened the divide. Some results even pushed the tension past the 5 sigma threshold, the gold standard for a genuine discovery in physics. The unsettling conclusion: this isn't a mistake. It's a clue. So where does that leave us? One possibility is that dark energy, the mysterious force accelerating the universe's expansion, isn't constant after all. Maybe it's growing stronger over time, or clumping unevenly like patches of mist in a valley. Others speculate about early dark energy, a fleeting surge of repulsive gravity in the universe's first moments that could have subtly altered Planck's starting conditions. Then there's the radical fringe. What if our universe collided with a neighboring bubble of spacetime shortly after the Big Bang, leaving behind invisible scars that skew our measurements? But the most tantalizing option is that we're glimpsing cracks in the standard model of cosmology itself. The model rests on pillars like Einstein's general relativity and the assumption that the universe is isotropic, the same in all directions. If either of those is flawed even slightly, the implications ripple across everything. Alternative theories like modified gravity or exotic dark matter particles that interact unexpectedly are suddenly back on the table. The Hubble tension isn't just an academic curiosity, it's a fork in the road. Resolving it could mean discovering entirely new physics or admitting that our cosmic yardsticks are fundamentally broken. Telescopes like the James Webb Space Telescope and the upcoming Vera Rubin Observatory are now racing to gather fresh data, hunting for systematic errors or hidden variables that might bridge the gap. But if the disparity holds, we might be standing on the brink of a revolution, staring into the abyss of everything we don't yet understand. One thing's certain, the universe isn't playing by the rules we wrote for it. And that's exactly what makes this tension so exhilarating, because in science, the moments that upend our assumptions are the ones that propel us forward. Whether the answer lies in dark energy, gravity's secrets, or something no one's even dreamed up yet, the Hubble tension is a reminder that the cosmos still has surprises up its sleeve. And the next big breakthrough might be hiding in the space between those two stubborn, conflicting numbers. Most planets are born into the orderly embrace of a star, bound by gravity to dance in predictable orbits. But out in the cosmic wilderness, between the glittering constellations, there's a class of worlds that defy this universal rhythm: rogue planets. These nomads drift through the void without a sun to call home, and in 2018, astronomers spotted one of the most intriguing yet, a rogue world roughly the same mass as Earth, sailing silently through the darkness. Finding something that emits no light and floats untethered to any star seems impossible, but nature offered a clever workaround: gravitational microlensing. Here's how it works. When a rogue planet passes in front of a distant star, its gravity bends and magnifies the star's light like a cosmic magnifying glass, creating a temporary brightness spike. By monitoring millions of stars for these subtle flickers, telescopes like Poland's optical gravitational lensing experiment, OGLE, caught the telltale signature of this Earth mass wanderer. The event lasted just a few hours, a fleeting blip in the data, but it was enough to map the planet's mass and trajectory with startling precision. What makes this discovery so haunting is the backstory it implies. How does an Earth-sized planet end up alone in the interstellar void? Some theories suggest it was flung out of its birth system during the chaotic gravitational tugs of giant planets, a cosmic slingshot event that left it homeless. Others speculate it might have formed in isolation, a lone wolf condensing directly from a collapsing gas cloud too small to ignite into a star. Either scenario paints a dramatic picture: a world that never knew sunlight, where the only warmth comes from radioactive decay deep in its core, and the sky is an eternal, starless black. The implications ripple beyond mere curiosity. Rogue planets could outnumber stars in our galaxy by a factor of 20, according to some estimates. If even a fraction of them resemble Earth in composition, they might harbor subsurface oceans kept liquid by geothermal heat, dark, hidden biospheres where life clings to existence without photosynthesis. Imagine extremophile microbes thriving in underground reservoirs, or exotic ecosystems fueled by chemosynthesis, like those around Earth's hydrothermal vents. The possibilities rewrite the rules of where life could persist in the universe, yet the biggest question remains unanswered: how many more of these lonely worlds are out there? New telescopes like the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will scan the galaxy with microlensing precision capable of spotting thousands more rogues. Each discovery will peel back another layer of this cosmic mystery, revealing whether our solar system's orderly architecture is the exception, or if the universe is teeming with untethered Earths, adrift but never truly alone. This rogue planet isn't just a scientific oddity, it's a mirror held up to our own world, a reminder of how fragile planetary stability can be. One gravitational nudge, one cosmic accident, and even a planet like ours could find itself cast into the endless night. And that's the unsettling beauty of discoveries like this. They don't just expand our knowledge of the cosmos, they reframe our place within it. For billions of years, the cosmos kept one of its most precious secrets hidden, where heavy elements like gold, platinum, and uranium are born. Then in 2017, astronomers witnessed a cosmic alchemy so violent it could only happen once in 10,000 years. Two neutron stars colliding in a blaze of light and gravitational waves, forging enough gold to outweigh our entire planet in a single cataclysmic instant. This wasn't just another stellar explosion, it was the smoking gun, confirming that the universe's most valuable elements are minted in the heart of these unimaginable collisions. The event, catalogued as GW170817, began when gravitational wave detectors LIGO and Virgo picked up subtle ripples in spacetime, the signature of two ultra-dense neutron stars spiraling toward oblivion. Within seconds, telescopes worldwide swiveled toward the source in galaxy NGC 4993, 130 million light-years away. What they captured became legendary: a kilonova, an explosion 1,000 times brighter than a typical nova, its light tinged crimson from the radioactive decay of freshly forged heavy elements. The data revealed something even more extraordinary: the collision ejected material moving at nearly the speed of light, a turbulent soup of neutrons so dense they fused into elements heavier than iron almost instantly. Here's why this changes everything. For decades, scientists debated where half the universe's heavy elements originated. Supernova could explain some, but the math never added up. Neutron-star collisions, though rare, turned out to be the missing piece. Simulations showed this single event alone produced an asteroid's worth of gold and platinum, scattering them into space like cosmic treasure. The discovery confirmed that the gold in your jewelry, the uranium in nuclear reactors, even the iodine in your body, all trace their origins to these apocalyptic mergers. But the real magic lies in the details. The kilonova's light curve, how it brightened and faded, betrayed the presence of a previously theoretical process called rapid neutron capture, or the R process. In this extreme environment, atomic nuclei are bombarded by so many free neutrons they balloon into unstable, oversized versions of themselves before decaying into precious heavy metals. It's a form of alchemy far beyond anything medieval chemists dreamed of, requiring conditions so extreme they exist only in neutron star smash-ups or the cores of collapsing supernova. The aftermath deepened the mystery. Follow-up observations revealed a faint, lingering glow that didn't match predictions. Some theorize the collision left behind a hypermassive neutron star, a short-lived object so dense it defies physics before collapsing into a black hole. Others speculate the explosion might have launched relativistic jets, similar to those seen in gamma-ray bursts, but viewed from an angle that obscured their full fury. Every new finding peels back another layer, revealing how much we still don't understand about these cosmic crucibles. What makes GW170817 revolutionary isn't just the science, it's the storytelling. For the first time, humanity watched as the universe turned energy into matter, chaos into creation, proving that even in destruction, there's artistry. Every gold atom carries the echo of that collision, a relic of neutron stars that died so we could hold a piece of the cosmos in our hands, and somewhere out there, another pair is circling, waiting to collide, ready to paint the darkness with stardust once again. Black holes devour everything that crosses their event horizon, but what if the universe has cosmic fountains to balance these drains? Enter the white hole hypothesis, one of the most tantalizing what-ifs in theoretical physics. Where a black hole's gravity is so strong nothing escapes, a white hole would be its mirror opposite, a region of spacetime where matter and energy erupt outward uncontrollably, forbidden from ever being reabsorbed. It's like hitting rewind on a black hole's nightmare. Instead of an inescapable pit, you'd face an uncrossable mountain where nothing gets in, but everything gets violently ejected. The math behind this idea isn't science fiction. Einstein's field equations allow for white hole solutions just as naturally as they predict black holes. Some researchers argue they could form naturally when a black hole's collapse reverses in extreme quantum scenarios, effectively bouncing back outward in a new region of space-time. Others propose white holes might be the secret endpoints of wormholes, spewing out matter that fell into a black hole elsewhere in the universe, or even in another universe entirely. But here's where it gets wild. White holes could solve some of cosmology's stickiest puzzles. Take the mystery of fast radio bursts, those bizarre, high-energy cosmic flashes with no clear explanation. Some theorists suggest these could be white holes burping up plasma after guzzling it through a black hole in the distant past. Even dark matter might get a new origin story. If primordial white holes formed in the early universe, their explosive ejecta could have seeded the invisible mass that now holds galaxies together. Yet for all their theoretical promise, white holes face one glaring problem: no one's ever seen one. The universe seems obsessed with creating black holes of collapsing stars, galactic mergers, even microscopic ones in particle accelerators, but white holes. Radio silence, critics argue they're mathematical phantoms, unstable in reality, collapsing into black holes the moment they form, but supporters counter, maybe we're looking wrong. A white hole's outburst would resemble the birth of a universe, something we've only witnessed once. Could the Big Bang itself have been the ultimate white hole event? The real value of this idea isn't just about proving white holes exist, it's about stretching our imagination. Whether they're real or not, they force us to ask deeper questions about time, entropy, and the universe's hidden plumbing. And if we ever do spot one, it would rewrite the rules faster than you could say, space-time anomaly. Until then, they remain the universe's most provocative thought experiment, proof that sometimes the boldest ideas come from running the math backward and daring to ask, but what if it works the other way? The edge of our galaxy isn't just an abstract boundary, it's a fortress. In 2021, data from NASA Voyager probes and the Hubble Space Telescope revealed something astonishing: a vast invisible energy field encircling the Milky Way, acting like a cosmic force field that deflects high-energy particles trying to enter or exit. Scientists call it the galactic barrier, and its existence challenges everything we thought we knew about how galaxies interact with the void beyond. Imagine the Milky Way as a bustling city, its streets alive with the traffic of stars, gas, and cosmic rays. Now picture an immense, shimmering wall surrounding that city, one that selectively filters what gets in or out. That's essentially what this barrier does. When Voyager 1 and 2, humanity's farthest flung emissaries, reached the heliopause, the boundary where our sun's influence wanes, they detected something unexpected. High-energy cosmic rays from outside the galaxy weren't flooding in as predicted. Instead, their intensity dropped sharply, as if slamming into an unseen shield. Meanwhile, particles from inside the Milky Way piled up against the same invisible boundary, like water against a dam. What could create such a structure? One leading theory points to galactic magnetism. The Milky Way's magnetic field, generated by swirling ionized gas and the motion of charged particles, might extend far beyond the visible disk, forming a protective bubble. But here's the catch: magnetic fields alone shouldn't be strong enough to deflect the galaxy's most energetic particles, some moving at nearly light speed. That suggests something else is at work, possibly tangled magnetic filaments or even dark matter interactions warping the fabric of local space. The barrier's discovery also raises a provocative question: is this unique to our galaxy, or do all galaxies have similar defenses? Observations of nearby galaxies like Andromeda hint at similar particle halos, but none as sharply defined as the Milky Way's. Some researchers speculate this could be a remnant of our galaxy's violent youth, a relic of ancient supernova explosions, or quasar activity that left behind a fortified shell. Others wonder if it's a dynamic structure, pulsing and shifting in response to external forces like the gravitational pull of neighboring galaxies. The implications ripple far beyond astronomy. If the galactic barrier filters certain cosmic rays, it could influence the chemistry of interstellar space, altering where and how complex molecules form the building blocks of potential life. It might even serve as a cosmic eggshell, shielding fragile planetary systems from the most destructive radiation the universe can hurl at them. Yet for every answer, the barrier presents new mysteries. Why does it block some particles but let others pass? Could it be linked to the Fermi bubbles, those massive, gamma-ray-emitting structures ballooning from our galaxy's core? And if it's truly a magnetic phenomenon, what keeps it stable across tens of thousands of light years? Right now, telescopes like the upcoming Square Kilometre Array are training their sights on the galaxy's edge, mapping magnetic fields and particle flows with unprecedented precision. What they find could rewrite our understanding of galactic ecosystems, or reveal forces at work we haven't even begun to imagine. One thing's certain: the universe loves a good moat. And the Milky Way, it seems, has built one worthy of its mysteries. From rogue planets drifting between galaxies to black holes that sing, from cosmic dust hiding on the moon to phantom stars made of dark matter, these 30 discoveries aren't just footnotes in astronomy. They're seismic shifts in how we understand the universe. Each one peels back another layer of the cosmos, revealing a reality far stranger and more dynamic than we ever imagined. Think about it. Phosphine on Venus forced us to reconsider where life might thrive. The giant arc challenged the very notion of cosmic uniformity, and that runaway black hole dragging a river of stars behind it. That alone rewrote the rules of galactic collisions. These aren't just incremental updates, they're full-scale revolutions, proving that the universe operates on a scale of wonder we're only beginning to grasp. But the real magic lies in what these breakthroughs promise for the future. Every anomaly, every paradox, is a breadcrumb leading us deeper into the unknown. Take Tabby's star. Its bizarre dimming didn't just spark debates about alien megastructures. It taught us humility, reminding us that nature's creativity outstrips our wildest theories. Or consider those interstellar meteors. Their fragments could hold secrets about how planets form around distant suns, offering clues we'd never get from our own solar system. And let's not forget the Hubble tension, a cosmic puzzle so profound it might unravel the very fabric of cosmology, pushing us toward new physics we haven't even named yet. What ties these discoveries together isn't just their shock value, it's their collective call to exploration. Missions like Artemis and the James Webb Space Telescope are already racing to follow up on these findings, armed with tools our predecessors could only dream of. The next decade could unveil life in Venus's clouds, pinpoint Planet 9's hiding place, or even capture the birth of a white hole. And with breakthroughs like time crystals and neutrino astronomy, we're not just observing the universe anymore, we're learning to speak its language. So here's the takeaway: the cosmos isn't a static museum exhibit. It's a living, breathing frontier where today's impossibilities become tomorrow's textbooks. Whether you're an armchair stargazer or a seasoned scientist, there's never been a more thrilling time to look up, because somewhere out there, hidden in the data or lurking in the darkness, is the next revelation, the one that'll make us gasp, question, and rethink everything all over again. The universe hasn't finished surprising us, and that's the most exciting discovery of all.